Okay, I know and you know that there is no way to prove that I am doing this before seeing the solution. However, there's a cake problem. I have an intuition saying 1/3. Now, why is that? Well, here's the thing, right? If you have the cake with the candles in the middle, you're screwed for a majority of those positions. And so if you put the candles on one side or the other side, that equals the positions that we could say that they are equivalent. However, they correspond with different numbers. So, for example, 1 through 20 and 80 through to 90. All of that allows for a lot of positions on the one side, everything above 20, and everything below 80. So that equals a portion of the cake which is majoratively capable of being only cake on one half of the after the slice, like wherever arbitrarily they put the slice. So it could be that they slice it here or there or right on the end, but anywhere where there is candles, we're hoping that we get a slice with candles and a slice with cake. And so we've gone through this a little bit. Um, I have gone up to, and I'll be honest, 2 minutes and 30. And how could I prove that I'm honest? Well, let's just take a look at the camera where I left off. 2 minutes and 56 seconds is how far I've got into this, just so you know of my reference frame. And also, I should have done this with the other format so that we could have a bigger screen, and I hate myself a little bit for that. So we might do a part 2 where we're on the right format. That being said, let's start the premise.
Shall we? Look, I've even got a sign for you. 2 candles, 1 cake. So that is the new puzzle. The puzzle was originally set without a cake. It was a stick. I've deliberately got a linear cake. We have 2 candles. I like your choice of candles. These are fresh candles, unlit, and they're both blue. That might be important later on that we can't tell the difference. Although, spoiler alert, it's not going to be that important. And the puzzle is very simple, Brady. I would like you to imagine that the candles are placed randomly on the cake. There should be a klaxon going off. Like, what do I mean by random? I will tell you, I mean uniformly randomly on a line along this cake. I don't care about the sideways movement. Like, imagine there's a line along the center. The candles go in somewhere. If I wanted to do it, simulate it, maybe I could generate a random number from 0 to 1 in some uniform way and use that to mark how far on. So maybe that one goes there.
Personally, I don't think that sliced bread is cake at all, because sliced bread isn't crumbly like cake. Or is it? Anyway.
This one goes somewhere else randomly there. The puzzle now comes when you pick up a knife and you say, the cut of this cake, we're going to split it into 2 portions, happens also randomly. If I cut it here, then I'm not too worried about the unequal pieces. We'll just deal with the aftermath of that another day. The point I want to talk about this time is that there is not a candle on each piece. So the question becomes now a probability question. If the candles go on randomly and the cut is done randomly, what are the chances that each piece has a candle?
Okay, so here I started doing some brain work, and I was like, okay, well, the fucking minus numbers piss me off. Fuck you. I want to see how far I'm into the video, and I don't know. But on the tablet, on the iPad, I do know, so that's freaking stupid. And I have no idea how you can fix that. But the math would say that we are... Oh, for fuck's sake, I can press it. Whatever. Okay, fine. Thank you for that. 1, 2, 3. Okay, so we're not as far as I have been. Let's get to where I have been. Because...
I'm interested to ask your intuition, Brady. What is the probability of each piece having a candle?
Feels like it's going to be 50-50.
Why? I know I'm asking you why while you're operating a camera, and that's always tough, but...
It feels like the cut should be 50-50.
What about the cut?
It feels like when you average out where all the cuts happened after a zillion cuts,
The average is in the middle.
the average is in the middle.
I agree, and actually that's true of the candles.
Like, if you want to end up with a slice where when the slice happens, you end up with one side of the slice has candles and the other side of the slice has empty space, and then you need to figure out the distribution of what happens. But this is the tricky bit, is where the positions of the candles are. I immediately said that, like, if you think of the candles being very far apart, then, like, if they're at the 20 and 80 point, well, then it's less than a third. Like, you only have 40 spaces. Well, yeah, you have 40 spaces where every other space in the middle is both of them have a candle. And we were trying to avoid that, so we only have a third. So that was my first intuition. The other component was like all this stuff where all the candles are grouped in on like half of the cake, and then that's a different amount of numbers. And I don't know. It's just a thing I wanted to try to
Two,
see what
but
my
that makes it
guess
slightly
was.
less intuitive because they're all averaging to the same place now. So
And there's not something that I'm gonna be saying like some intuition, some like, oh, they're wrong or whatever. I'm just being like, this is interesting.
the thing I like about this puzzle is that at first glance to me, and I'm a mathematician, but I'm not. I'm not an A grade.
I don't
mathematician.
have
I'm a
to be
maths teacher,
disproving
really.
everything.
It feels to me at first glance I don't know how to start. I don't know how to start putting numbers on this other than my intuition. And a lot of people say 50% to me. They think that's so your intuition is like other people's.
Can I ask a question?
Yeah.
Is it possible to cut the candle? I'm assuming it's impossible to cut the candle.
I think that's a good assumption, and I love working with you, Brady. You're an excellent mathematical modeler. You are aware of the complications that could get involved, and you decide to make things simple. Now, once we solve this one, we could start having non-infinitely small point candles and do it, but I suggest we don't bother yet. This is what mathematical modeling is all right. Let's keep it simple until we've sorted the simple one out. That's the puzzle.
Yep.
If you haven't already paused the video and you want to think about it, now's a good time. What I'd like to do for this one is solve it
Yeah.
in more than one way. And that's kind of the point I wanted to talk about here, is that mathematicians solve things in more than one way. And that's almost always what makes some profound insight occur. Because if you can see it from one perspective and another perspective, you've got like a joining up at the back. And that's a nice moment.
Yeah.
So we're going to try that in this one. Other piece of problem solving advice, and for you as well, that if you're stuck on something, try a simpler puzzle. So if I took one of the candles away, my question has now no meaning, right? What are the chances we get a candle on each piece? Obviously, can't happen. So candle goes on, and I cut somewhere randomly. What are the chances it's on the left? The candle.
50-50.
It's got to be 50-50. It feels like there's symmetry all over the place. They're both random. And actually, the easy way to answer that, I think, is an ordering idea. Either the candle comes first, or the cut comes first. And there's no reason why one should be more than the other, so you've got to go 50-50. That gives us a clue for our first way of solving the problem. Hey, if we want to split this into 3 ways to solve this problem, here's part 1, ordering. So ordering solved the simpler version. It was either the candle first or the cut first.
Right.
So why don't we try some ordering argument? And this is where I probably have to write some things down. C for candle.
Yep.
Oh, do I differentiate between the two candles? This is the other problem mathematicians have, is like, do I need to model them as different? And we've got 2 candles that look identical. So I'm just going to say they're indistinguishable. So let's say the candle could come first, and then the other candle, and then the cut. That would be one way of ordering the outcome.
What are you going to call a cut?
They're
We
all
can use like a V shape for a cut, or a K.
K for knife?
Yeah. I mean, it's an annoying initial letter to use, frankly.
I like K for knife because
K
a
for
K is what is strike in baseball as well. So
That is one possibility. I think this is where your instincts from the simpler one kick in. You realise, well, there are other possibilities, and they don't feel like they should be any more likely or less likely, because these are all random. Candle, cut. Cut with a K is now going to be in my head forevermore. What else could happen, Brady? And this is where I'm patronising.
you could do the knife and then the 2 candles.
Yeah, and that doesn't feel like less likely or more likely. Is there another option?
Yeah, you could.
I don't. Here's the thing, right? Order of events doesn't change distribution in my brain. So, like, you might be able to get more intuition after the first cut. Like, okay, after, if you look at the cuts, then um, you automatically know any distribution on this side gives you a lot of information, and then like that's just a lot of easy, and then you can just go through it. But then
Do a candle, a knife, and a candle.
And that's the one that sort of answers the question I started with. Is that's the only time we're going to get a candle on each piece. And since all of these are equally likely, although I haven't done a strong sort of careful argument
there's
for
no
that, but it
difference. I
feels
don't
like it's
see any
believable that
difference.
one should be not more likely than the others, which means that we get a third for that, a third for that, and a third for that. I now think this is one way of claiming that the answer to what are the chances we get a candle on each piece is a third. Which isn't a million miles from your 50%. But what I liked...
It's quite a way.
Well, I'm trying to be kind. The intuition for the single candle one, however stupid a question it is, it feels like a dumb question, but it's much more strong intuition for me that that's 50%. And then when you upgrade to 2, you feel like, well, maybe it's less likely, and so if I'd given you the chance, I'm sure you'd come down. Anyway.
Technically, there is no difference between this and simply having 3 separate candles, where instead of just have the third candle be the last distributor, and the placement of then it becomes harder to figure out like what exactly is actually going on reference to each other. Um, so what are the odds? Like, how would you even bound that? So cuts make more sense than a third candle instead of not cutting for some reason, because obviously there is the direct divide, and then it's all just like right there in front of you. Makes sense.
Maybe that's right, and maybe it's not. There's another way to solve this, which maybe feels a bit more mathematical.
Okay, here's the problem. The problem with my thought about it is not about cut, candle, cut, or any of those positions relative to like each other. That's actually like a false intuition. It feels like that's not something that's going to give you anything correct. What instead will give you something correct is um just just thinking about 3 different numbers, 3 different candles, and then um what are the odds that those 2 candles are going to be next to each other, and the other candle is going to be not between or something? And then if you voice it that way, then I think you have a better understanding of how to approach this. But candle those 3 possibilities actually don't change distribution whatsoever. That's an illusion. So whoops.
But the key to this one is that each of those options was equally likely. Otherwise, you can't make an argument. I guess we should mention
Yeah.
there's a danger in every probability question about this. Like, what's the chance you win the lottery? One argument says you either win or you don't. So it's 50-50, right?
Yeah.
And obviously, the misconception there is that they're not equally likely. So whenever you're making
Obviously, there are 2 types of lotteries. There is the one where it can be 50-50, and then there's the one where you actually have to think about all the different potentials that could occur, and then that determines the actual probability of it happening, which is 1 out of a giant number.
argument about probability from studying cases, you better check that they're equally likely, which I think we have done.
And that would have been the same if we numbered the candles. We had candle 1 and candle 2.
I'd forgotten about that, and you're right to pick me up on that. I'm glad you asked. So let's say I did candle 1, candle 2, cut or knife, whatever we call it. Now we've got more options. So maybe if I mark these, that's a 1, and these are the best numbers you've ever seen Almost as good as my mouse from a long time ago. Now there's another option, right? With the cut over there, I could have a candle 2 and candle 1, and these would switch round, and that would be a different option. But by a similar argument, you might see where this is going. There's no reason to say that one's more likely than the other. And so actually, the other option you said, cut to candle, could be these two, and you can see how this is going to pan out. And now we've got 6 options, each of which is equally likely, and 2 of them satisfy our conditions. So I still think we're in a third, and it's nice to know that
I
if you're
still
worried about
don't
whether the candle
agree.
I know some of you.
You can't use that logic.
It doesn't. The argument works both ways around. Hey, that's already 2 ways, and that was only part 1. Method 2. Let's do another way of solving it, because if it comes up with the same answer, we're golden. If it doesn't, we've got to ask questions about at least one of the methods. So method 2.
First
I was
method.
mathematical on this. I said that these are 3 decisions. There's a candle, and a cut. Let's represent each one of those random things by a number. So candle 1.
Listen. Okay, now we're getting to the weeds.
Is a number between 0 and 1, uniform random distribution. Candle 2 is a number, 0 and 1. And the cut is a random number between 0 and 1, which tells me where it will land. Now, if you have 2 numbers, you could draw a 2-dimensional picture of what could, like, you could have one dimension and the other dimension for the other number. So if you have 3 numbers, like in our case, we need to draw a 3-dimensional picture of the outcomes. And actually, what I'm talking about is a possibility space, but it's going to be a 3-dimensional picture. If I start drawing it on here, being able to draw in 3D is a surprisingly useful skill for a mathematician. And I'm not doing a geometry problem here, but I'm drawing a probability space. So that's X, Y, and Z, if you're in England. And let's say X is candle 1, Y is candle 2, and let's say Z be the knife. Somewhere between 0 and 1 on this axis. Somewhere between 0 and 1 on this axis, and somewhere between 0 and 1 on that, will describe the situation we end up. So what we've actually got is a cube. And any arrangement we've got here is a point within the cube. I mean, I can hold one, right? So a point in this cube represents the outcome of our randomness. And we can simulate this nicely on GeoGebra.
Of course.
Of course, I really like GeoGebra as a sort of tool for tinkering. And what I did here was I drew my cake, and I've got a line that I can cut. So I can choose where the cut goes, I can choose where candle 1 goes, and I can choose where candle 2 goes. And you can see that over on the right, it's moving things around. So actually, let's make this spin a bit so we can see what's going on. The x-axis for candle 1, the y-axis for candle 2, and the vertical axis for the knife. And all 3 measurements give you where the point is in space. If I put the cut somewhere in the middle and the candle over on the left here, can you see that this point I'm representing in the 3D space is gone bold? And I've got a little announcement here saying cut is between candles. You can see that from the cake, but if I put the other candle over here, it hasn't gone bold. So basically, there's a whole region of the cube where we've got a success, and there's a region of the cube where we haven't got a success. So I'm just going to colour in the cube the points where the cut is between the candles. And I think you might be able to see where this is going in terms of get a probability out of it, because the entire space is all the possibles. And those 2 regions, it's necessary to spin this to see what those regions look like. You can imagine those are the regions where the knife is in between, and it's really narrow in the middle. If the candles are close together, there's not a big region, and it's wide and the candles are further apart. So the only question now is, what volume of the cube is shaded? What proportion? It's not trivial, but it's also not that difficult, particularly if I spin one of these regions without turning. I promise you I'm not transforming. I'm just going to spin it around.
Yeah,
and we
it
get
looks
a
more
square-based
like
pyramid,
1/3.
in fact. It's occupying one side of the cube and going to a point. In fact, here's a cube, right? And if I pull one of these off, this is the shape we've just made. Now, the way I've configured it, it didn't automatically turn into this shape, but here's that volume. And I don't know if you remember the volume of a pyramid, Brady. There's no reason why you should.
So that base times height?
Base times height gives you the volume of a cube. Cuboid.
And then what do you a third?
It is a third.
Yeah.
And this cube was volume 1, so this volume is a third. Which is a relief, because that's the number we got earlier. And what we've done is we've proved this in 2 different ways. We've done it by an ordering argument from our paper earlier.
Yeah, but the approach I went was literal brute force of all positions. It, like, certain initial states seem to be leaning towards 1/3. So, yeah.
And ordering in space, not time. And we've done it by a geometry argument, which is the volume of a cube. Now, the one catch is, what if you didn't know the volume of a pyramid? And so here's my point about solving things in 2 ways. What I like about this by accident is that we're solving a probability.
Okay, here's the other okay, no. The size of that triangle relative to the cube and all of that there are ways of like reordering it so that it can become, so like if you don't have the volume of both of them and confirm, it could be 1/4 and you can't visually see it, so you have to do some like other stuff and get that right. Like you pulled some numbers of 1/3 out of the air because of triangles or pyramids, but that's not actually relevant because, again, that size of a triangle compared to a bigger cube is a smaller percentage of the possibilities. So it could be a triangle stuff or pyramid that represents only 1/8, and you would be completely off. What are we doing?
We did it with ordering, we did it with geometry.
I
And if I
said I
don't know what the
wasn't
volume
going to
of a square-based
second
pyramid
guess them.
is, I can prove it to you by probability.
Okay.
I'm saying the answer is a third, so the volume of this shape is in fact the third of a cube. And hey, a proof of the volume of a square-based pyramid via a cake-cutting exercise. This is a serious point. If you can solve things in more than one way, you have two perspectives, and that's quite often a moment of profound insight. Like that's when mathematicians get excited. You have two different ways of looking at a problem. Worth mentioning, there's another way of proving these fit together to make a full thing, and there's three of them. If I lock them together, these are 3D printed, then they obviously make a cube. Now, that's not a mathematical proof, but it's pretty hard to argue that those three shapes do make a cube, and therefore, if they're identical, they are a third each. So we've done it the two different ways,
Right.
but I promised there was deep water here. Maybe this isn't so deep. It's a profound moment to do things from two ways, but there's at least another way of doing this and a glimpse of why questions like this are maybe more dangerous than you want them to be. I'm going to refer to something which you talked about with Grant in a recent video about Bertrand's paradox and how thinking about cake led me on to thinking a lot about what you and Grant talked about. So the third way of solving this, and this is a nice thing for all mathematical problems, is instead of theorizing, just do it. So
Which is what
you're
I
going to
did.
record 1,000 takes of me. Just no, we're not going to do it. The trouble is, this is where you start noticing. How would you actually pick a random point for the candle without like a random number generator? It's a pain. So without cutting the cake and spoiling our tea break later, we'll simulate it. What mathematicians might call a Monte Carlo method, but we'll simulate it because if it doesn't give us a third, we start to doubt all the theory, which we've carefully proven twice. So let's simulate it. So apologies for the crudity of this model. I feel like I'm quoting Doc Brown there. But this one's not a scale model of Hill Valley. This is a scale model of a rubbishy rectangular cake. I've got two tiny candles on here
I
and cut.
appreciate
And all
that.
it's going to do, if I click on one of the buttons here, it's just going to pick random positions for each of them. And you can see this one, there's a cut just in between the candles, success, and it's going to count them. And I'm not going to keep clicking. I'm just going to let it go. This isn't rigged, but it's done 50 odd trials now. It's not doing it super quickly, but we've got a success rate ticking away up here that is relievingly, to me as a mathematician, settling around about a third. Now, I wouldn't expect it to be really tight on a third until I've done thousands. And it actually always surprises me when I do models how long it takes to converge on what theory is. Even if I believe the theory, it takes a long time for randomness to back it up. But it's not bad. I mean, this feels like I have rigged it, but it's settling about 0.34. But this is
Yeah.
backing us up, which is a relief. So the two ways of solving it don't feel like they've had any crisis of conscience. And the experiment, however computery modelled it is backing us up. Slightly above a third at the moment.
Unfortunately, the first method is not informative whatsoever. The second method is a little bit better. And then obviously brute forcing is, which is weird because my brain just brute forced it without a computer. Just imagining distributions of, like, here's the thing. Instead of brute forcing it with randomness, you start with candle on the one side, candle, random position, cut, right? How many of the spaces can you still have that amount of cake that is on the other side of all of it? So we start with the two candles are on one side of the cake. The cut is over anywhere on the right for that position. And so we just take those numbers and increasing the numbers, and then we get a certain amount of positions that can actually give you the result. And it's better to work that method because then you work full length 1, full with the move the candle over, full length 2. But the other problem, of course, is when you have to work. But of course, here's the thing. Once you get to like the middle, then it becomes symmetrical and you don't have to worry about doing the other half of the equations because it's kind of the same. So once you've gotten halfway there, you're solved, kind of. Um, yes, both sides being symmetrical, being once you've done half of the cake, you've solved for all of it. So what I figured was, again, for the number of positions where it can be that you have potential area of cake, and then as the candles move, how much less cake you have each time, something, something. I don't know. I settle on a third because of actually just looking, and it's like, no. If you have the candles in the middle, if you have the candles on the right or on the left. And I didn't need too much more after that. Possible positions of the cake and candles, possible positions of the cut. And instead of thinking of here's the big thing. Instead of thinking of the two candles as separate entities, think about a volume which includes that length of cake between the two candle pieces, and then it just way more simplifies because you don't have to think of two candles. It's just there is a volume over here. The rest of the volume is a potential where there is a cut, and then you don't have this volume inside of that cut on that side. So as long as you can make those types of volumetrics, and you didn't mention that as a possibility, I'm going to have to make a comment.
Trouble is, when we upgraded this problem from sticks to cake, it feels very natural for me to then, in my head, upgrade from linear cake to a proper cake. So I started asking the question, what happens if you do this on a square cake or a round cake, which feels much more traditional? And I scared myself slightly.
If you'd like to see Ben.
How do you spell volume? Like, not volume as that, but a volume as in, is there a difference between the word volume and volume? Let me look! Okay. So volume. Okay, so it is the same difference. It's the same spelling. I didn't realize it would. Okay, anyway. Um, Oh, you gotta blow your mind. It doesn't matter if the volume moves within the cake because of the distribution. Okay, technically it doesn't. Yes, because the outside volume of the cake that you can have all these potentials equals, like, let's say that you have 50% of the cake volume are represented in the two edges as a candle. It doesn't matter where in that cake you put those candles, there will be 50% of the cake left on the outside of the two candle volume. So that's a much easier working with it as a volume and volumetrics thing. Then it becomes way simpler. Holy crap, so simple. Oh God. So yeah, all you have to do is then increase the volume of the area of the two candles, and then um, the third point just lies outside of that volume, and it can be arbitrarily different spaces and pieces and whatever else. But if you're comparing the potentials, like there has to be some amount, like let's say it's 1 to 100. You can figure out the portion of the volume of the two candle area in comparison to the rest of the area. Because if it starts off as, well, the two candles can only be as small as a single point, then the volume can be only as small as 2. And then everywhere else is 98. And you increase it by 1, then the volume is 3, and the remainder is 97. Change that up to have the volume just increase and expand all the way out until finally you end up with the distribution of, and it would seem like the volume should potentially be half, but then, like, we ended up resolving to thirds in two different methods that I don't condone, or the first method. Um, so, and my first intuition is a third because of the positions of the candles, and then I realized that the positions of the candles are irrelevant, and it's just a changing volume. Like, this is why I think you don't need to think of. But here's the thing. Right, this is why you do need to have it where the volume changes size from left to right and also from right to left. They're equivalent, but it's an equal amount of the positions, but it's like the problem then Oh God, this is nutty. Um, the problem then, yeah, I'll just leave that comment. I don't think I need to go further, but okay, so imagine you have the volume and the thing about the volume moving is that it all cuts on like one side of it. Well, oh, it breaks my head because if you have the cuts on one side of the volume, it the volume of the candles and the volume on the outside are included in, and so it drastically changes the amount of cake or whatever, something, something, something. But it doesn't change the number of. So what was the answer? The answer, if you think about it in the volume method, as the volume of the two candles increases, like even with the thing is, if you have the area where the candle volume is in the middle, right? Then you can't cut in that area, and so you have to cut on the outside. And there are more positions where, like, if you have the candles on the furthest spots, then there's nowhere you can cut where you won't get both slices having a candle. So the closer you get the volume to like the middle, I end up wondering what the difference is between the distribution on the one side and the other side is. Because, and this is why when they talked about the idea of a one candle scenario, then you can just think of it as, well, it's obvious, it's just, it will never be that there will be two candles because there aren't two candles to start with. Or in the scenarios where the candles are very close to each other, then there are a lot of scenarios where it can easily be you cut it. In fact, there are zero scenarios where there are just as much as with one candle, with two candles and smaller amounts for the volume, then it becomes really easy to have a piece that is not candle, right? I don't know. This hurt this hurt a little bit to think of. And the randomizer is okay. I'm not gonna bother with that. I just wonder if, like, thinking about it as the volume of the two candles versus the line, which is the segment where you cut the thing off. I hope they see that and they say, wait, that's actually brilliant. What the hell? I need to get this guy on. Like, I'm hoping. But, um, but seriously, as the first idea with the three, this is wrong. this does not actually like rigor, because it doesn't matter the order of events. All situations being equally likely, it's not about order. Okay, this is about order of events, but it's about when the scenarios can happen, this equals, yeah, this does equal distribution. If you think of distribution, then it's fine. If you think of ordering, it was completely wrong to think of ordering, and then you'll get the correct intuition about it.
That and a third for that. I now think this is one way of claiming that the answer to what are the chances we get a
Strike in baseball as well, so.
that is one possibility. I think this is where instincts from the simpler one kick in. You realise, well, there are other possibilities, and they don't feel like there should be any more likely or less likely, because these are all random. Candle, cut. Cut with a K is now going to be in my head forevermore. What else could happen, Brady? And this is where I'm patronising.
You could do the knife and then the two candles.
Yeah, and that doesn't feel like less likely or more likely. Is there another option?
Yeah, you could do a candle, a knife, and a candle.
And that's the one that sort of answered the question I started with, is that's the only time we're going to get a candle on each piece. And since all of these are equally likely, although I haven't done a strong sort of careful argument for that, but it feels like it's believable that one should be not more likely than the others, which means that we get a third for that, a third for that, and a third for that.
Like I said, I only went to 2 minutes and 30 something seconds. I thought of a third that kind of makes sense because of distribution of candles. But the problem is with the cut, like, you can, when you have, yeah, no, the problem with this is that you can have, you can still put a cut on this scenario, like on here, on the outside of the two bounding areas, which is why I transform it into a volume and then just move the volume around and make cuts. So that means this intuition is possibly wrong, but then you got the randomizer, which makes it seem like it's correct, and just brute forcing it at that point, sort of. But then
Here in a cut, and all it's going to do, if I click on one of the buttons here, it's just going to pick random positions for each of them, and you can see this one, there's a cut just in between the candles, success, and it's going to count them. And I'm not going to keep clicking, I'm just going to let it go. This isn't rigged, but it's done 50 odd trials now. It's not doing it super quickly, but we've got a success rate ticking away up here that is relievingly, to me as a mathematician, settling around about a third. Now, I wouldn't expect it to be really tight on a third until I've done thousands. And it actually always surprises me when I do models how long it takes to converge on what theories. Even if I believe the theory, it takes a long time for randomness to back it up. But it's not bad. I mean, this feels like I have rigged it, but it's settling about 0.34. But this is backing us up, which is a relief. So the two ways of solving it don't feel like they've had any crisis of conscience, and the experiment.
so obviously the randomization is one thing, but then I still end up wondering, what if you do change it into a volumetrics thing, and then you just the like randomizing gives you a bunch of different like distribution of the potential scenarios, and that can kind of lead you in the right direction, or it can be correct. But I'm still wondering, like, as the volume of the area of the candles increases and the amount of cuts that you can make on either side changes, like, I still think the position of it doesn't change things, actually. So it's just the volume is getting bigger, the cuts that are valid amount gets smaller, and so it's like there's like a log or something that you can probably use to do the remainders as as the area of the candles increase, the potentials become smaller for the possibility of valid cuts, which only have candles on one side thing, cuts that are not in the volume of the candles area. Yeah. I still think I'm... What is a part 2? Cool. And this
I'm
is...
Professor Idris.
Okay, so here's the thing, right? This is years ago, so you gotta wonder, like, how long, and then I never made a response. Did I make a response to this video? Oh God. Years ago? Yeah, oh God.
Welcome to ServiceNow University, a playground for learning that's personal.
This is part 2 of a video about 2 candles and a cake. I imagine it will make more sense if you've seen part 1. So check out those links.
Real cakes are not linear, unless they're Battenberg cakes. I think they've got Battenberg, the linear thing. And there's a tradition of mathematical puzzles with Battenberg cakes. But anyway, real cakes look more like this. This is a nice lemon drizzle. I appreciate your choice.
We did, by the way, everyone, we did buy a Battenberg. We did buy a Battenberg, but we're not using this one.
We'll solve some other mathematical puzzles with that one, or just eat it.
Yeah. All right.
I wanted to upgrade because the original puzzle with twigs, and you don't upgrade a twig to a two-dimensional twig. So it's nice to comment that upgrading a puzzle purely for aesthetic things to set it as a nice puzzle also had mathematical consequences. I've got to put a random candle and a random cut on a two-dimensional surface, and then suddenly it's less obvious to me how you put a candle or a cut on a two-dimensional thing. Before I had many panics about this, I thought I'll just run a simulation rather than trying to solve it on a two-dimensional cake. So I got a GeoGebra file to do a square cake. It was easier to draw before you criticise my model. In hindsight, I'm going to mention very carefully how I chose where the random things go, but I didn't think hard about it at the start. I just picked a random X coordinate, a random Y coordinate for each of the candles, and for the cut, I picked a random X and Y and a random angle. And I thought that's definitely a random cut, and I was fine with that. And I ran my simulation, which I haven't made it look particularly pretty, but if I do run it again, it ends up converging to about a third again. And I was like, well, what's really nice about the one-dimensional one, it upgrades to a two-dimensional one, and cakes work, and this is just above a third at the moment, but it's 0.3 something, fine. And I went and did a talk about this at Maths Jam annual weekend, and everyone was nice about it, and we had nice conversations. And in the back of my head, I was like, this is a little mathematical bug saying, are you sure you know what you mean by random when you're in not just a uniform distribution? And I wasn't sure, and I didn't think about it because I was kind of naively lulled into a false sense of security because the number was what I wanted. But it turns out there are other ways to randomly assign a cut. And if this is sounding familiar with something I alluded to earlier, your conversation with Grant about Bertrand's paradox was precisely about pick a random cut or chord on a circle. So forget the square cake, which we could go and do the model with again, but let's upgrade to a real cake, definitely a circle, and I've got to put the candles on at random, and actually I'm happy enough that choosing a place for these to go at random is actually doable, although you can do it in several methods and it's not obvious which one's best. Let's just spray points on like I did before, random X coordinate, random Y coordinate, and if they're outside the circle, reject them. So we'll get a random point on the cake, and that's a good way of uniformly spreading the points out. But it's the cut that's a problem, because what we're doing is randomly choosing a chord, pick two random endpoints like this point and this point, that would define that cut, because any chord is defined by the two endpoints. Alternatively, though, you could pick a random point in the circle, a bit like I did with the candle, like this one, and say that's the midpoint of a chord, and any point uniquely defines a chord in that way. But it's a different distribution of cuts, and this is where you start getting into deep water. The nature of random is not as simple as you want it to be. Go and watch Grant's video for a big discussion about it, but what I did do was simulate the cake and candles cut problem with round cakes, and several different choices of how to do a random chord. I really enjoyed the conversation you had with Grant, because you were annoyed that it wasn't well defined, and I think mathematicians do have that sense of annoyance. You want things to be neat, but probability questions are often more philosophical than we want them to be. So this is a video of me choosing the two endpoints on the circumference, and the orange trace is where the chord's gone. I don't know why I picked this color scheme, but I liked it, and I ended up just mesmerized by the image. The thing is, the distribution is maybe not where you expected. It's kind of clustering towards the edges, and the middle is slightly less sparse, but it is quite uniform. So maybe this is arguably a good way of getting uniform cuts. But there's another way of choosing the cut. It's not a third. It's actually settling down to be about 0.16. That was after 10,000 attempts. So I believe this. If you choose a cut by this method, which if we're going to do it for real life, the real context would be like we put a spinner, we do a couple of spinners in the middle, and wherever it pointed to, we mark an endpoint, and we cut there. It looks like we get about 0.16 of the time we'd get a candle on each piece. And that's not a third. It's not even close, which kind of upsets me.
It's almost a half of a third.
It's almost a half of a third. Is it near to an eighth as well? But this is why the Monte Carlo methods and the simulations don't give you that sort of theoretical. They confirm theory quite nicely, but this time it means my theoretical thing has just not matured enough to sort it out. And if you run different simulations, here are just the pictures of what happens if you choose the cuts in different ways. So this cut is where you choose a random midpoint for the chord, and you see it hardly ever cuts, or just less often cuts near the middle. And that's a good reason why we're getting different probabilities. This one ends up being settling down to about 0.19. This one over here is choosing a random radial point, so that's choosing some distance along a radius and some angle around the center to go, and using that as the midpoint. Different distribution again. And this one's doing what I did on my naive version of the square, a random point and random angle, adding more randomness. This one ends up to be 0.3, close to a third, but not close enough. This one ends up being 0.325. My main conclusion of this is that I don't know what's going on. And it's sometimes nice to be mystified as a mathematician and realize that the real world of random distributions in 2 dimensions and in the situations like Grant discusses in his video is more complicated than you want it to be. We need to be careful about probability. I think, in summary, though.
Okay, here's a major problem with a lot of this, is randomness can be a lot harder to truly get right, because here's the thing. You get those lines, then you have an area of just a line to avoid. All the area that you can cut off of the cake on either side is the majority of the cake. So that's a large amount, but also you can cut it from the top down so that the edges of the dimensions also don't fall in, and then you end up with an extra number of cuts that you can have which don't include that area of a line. So just using a line gives you one bit, but then if you have 3 candles representing the area of a triangle, or 4 candles representing the area of a square, or other weird, then you're getting into weeds, because triangles are obvious. 4 is where it gets really complicated with this shit, because the 4 doesn't have to make a square. It can make any kind of trapezoid. It can make things that have weird shapes and squiggles, and so all of that is like a whole other thing. And again, they can have arbitrary sizes for the amount for all of that. But when you're thinking about the 2 points of the candle, and you think about that, they form a line. So in order to really avoid the candles being on both sides of the cut, you just have to cut around that line. So literally everywhere other than the line. So I don't understand why you're getting like a 0.1 or something. It should be a 98.7% success rate. Because except for like, well, if you only consider one axis of the cake, right? That's how much success rate you can have there. And then as you change the angle of that line, and you keep the angle of the cut consistent, then you will have a true analyze it this way, analyze it that way, analyze it that way. And then you have, instead of the line taking up only, like if you have a vertical cut, right? In order to avoid the line, you now have to avoid an entire volume, which is not just the area of the line. It's whatever area that line takes up. Like if it goes from here to here, then you can only cut on the outside of that line for the entire cake with a vertical cut. So, like, no vertical cut in that volume is valid, right? So that makes it into a third for that specific angle. Changing the angle again and make it more vertical, obviously you could go anywhere over here, anywhere over there, and it's all valid. So that's like 98.7%. You can't, or whatever. Like almost 99% of the cake can be cut, and then you'll end up getting one cut with both candles and the other cut with no candles. Um, so changing the orientation of it manually and then repeating the same vertical cuts gives you different information. And then so that would be the rigorous brute force method, where the candles are maybe in the corner, then all of it is valid. The candles are distributed throughout. And again, I don't distributed with like a line. And even if it's here, you still have like 99%. Here, 99%, 99, 99, 99. A bunch of these scenarios are 99% accurate. For half of it will be cut with cake and half will be cut with. It's only when you turn from a line that is, now that the line is actually taking up part of the cake, then it becomes each one of these positions has, where it's only this part of the cake, this small bit here. You can't take anywhere in that, but you can take everywhere over on this side, right? And then as you move, you have this distribution that literally follows the volume area for that vertical cut. And then as you change the orientation of the lines, that's how much. And then you increase the volume, change the orientation of the lines, change the positions. That's a rigorous thing that can just do all of that. But then it's not randomness. It's just distribution amounts. And so it should be like just a slider that can slide through the whole thing and then just give you the numbers. And then the success rate for this scenario and n scenarios gives you the total answer, which all describes just different amounts for this volume where it takes up this much of the cake. And so all of these are invalid. And then this much of the cake, so all of these are valid. And then even if the volumes are, the candles are as far apart as they could be, it's still 99% on a vertical cut. It's when you turn that, then each one of those different amounts can be like the whole thing is covered, there are no valid points. Then as you turn it, more valid points show up. Like it's this distribution, that distribution, and so on, right? You can imagine the amount of cuts that you can do on this side of it that can avoid this area. And same if you have it here or if you have it there. And so I don't know. It's hard with a two-dimensional space, but also it's hard with it. The area of a triangle actually converges into the area of a line because it's only the area of the longest line on that triangle, and just also includes areas of a shorter triangle line or shorter, just smaller amounts of space where the bulge occurs. So there's like slightly differences, right? Where the minimum cannot be a line, the minimum has to be also this area of an indent leading out that way. Where the line is the longest area of the triangle, and then the triangle is um, like infinitely tiny and squished, right? So it's just really whoop versus whoop, you know, infinitely wide in that sense. And it's like, so all of those things with distributions and that is like you just add that ignoring the length of the triangle, it just becomes the area of the bulge. And then as you change the triangle, then it becomes obvious that it would only be the area of the triangle, and it just reduces down still to just the line, which means the line is the more simple, obviously, but also it is also just as equally complete doing the line scenario as the triangle scenario. Again, once you get into 4 dots or 4 candles, well, then they could take up the entire area of the cake. They could take up the entire majority of the cake, but in the area of circumference, then they can never take the entire area of the cake. It's impossible. The biggest area you can take is like a diamond shape or a square shape out of the circle. So you still always end up with the maximum is the biggest square you can make inside of a circle, and then all just cut out that square volume, and then the area of the circle that remains is the distribution of all the cuts that can happen to give you no candles on that side of the cut, all candles on the rest of it. And so you have all those different options, and it turns into like everything other than that, you then have distributions of all the different areas where if it's like a dot here, a dot here, a dot here, and a dot there, then the diagonal axis becomes more open and you have more potential and you can just slide that along. And as it goes inside, all of those potential of the candle inside cancel out because they're the same distribution for this entire set. And so it reduces down to just the area of the triangle again. So it's only of some of those distributions where the candle is on the outside of the triangle part that you have another value that you have to consider, which is fun. And yeah, It only gets complex at 4 candles. And what's the point of talking about this? Well, it's interesting. It's neat. And it's like without even using the calculations and the distribution systems he has, I'm like, hold on, stop. No. It's just if you have this line, 99%. What did he even say?
So I believe this. If you choose a cut by this method, which if we're going to do it for real life, the real context would be like we'd put a spinner, we do a couple of spinners in the middle, and wherever it pointed to, we mark an endpoint, and we cut there. It looks like we'd get about 0.16 of the time we'd get a candle on each piece. And that's not a third.
Honey, that's not the argument. That's not even close to the argument. What? The original argument was to have the candles be on the outside, cut with candles, cut with no candles. Now you're saying the candles have to be on the inside? You inverted the puzzle. No. Okay. Stop. No. 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 This is not okay. No, that's false. That's just bad science right there. Oh my God. I still like the video.
It's not even close, which kind of upsets me.
It's almost a half of a third.
It's almost a half of a third. Is it near to an eighth?
I was not doing candles on each piece. I was everywhere other than candles on each piece, which means, yeah, the distribution of the candle's potential is then really small. Yeah, that makes sense. It'd be like 10% or whatever.
But this is why the Monte Carlo methods and the simulations don't give you that sort of theoretical. They confirm theory quite nicely, but this time it means my theoretical thing
literally
has just not
changed the
matured
puzzle.
enough to sort it out. And if you run different simulations, here are just the pictures of what happens if you choose the cuts in different ways. So this cut is where you choose a random midpoint for the chord, and you see it hardly ever cuts, or just less often cuts near the middle. And that's a good reason why we're getting different probabilities. So this one ends up being settling down to.
So here's the problem, right? Cuts in the middle only happen. Like, why? Why would that happen? Like, is the definition to try to find, again, a cut which gives you a candle in each piece? That wasn't the original puzzle. So, what is going on? I don't.
At 0.19. This one over here is choosing a random radial point, so that's choosing some distance along a radius and some angle around center to go, and using that as a midpoint. Different distribution again. And this one's doing what I did on my naive version of the square, a random point and a random angle, adding more randomness. This one ends up to be 0.3, close to a third, but not close enough. This one ends up being 0.325. My main conclusion of this is that I don't know what's going on. And it's sometimes nice to be mystified as a mathematician and realise that the real world of random distributions in two dimensions.
Well, okay. First of all, you change the definition of the result that you desire, which changes everything. You're now saying you only want this, which is not the same as you want candles on one side, cake on the other, no candles. Right? And then, like, The other, obviously, fourth-dimensional puzzle of this is how many times can you cut the cake and not include any candles in the cut that you actually distribute, leaving an area of cake which only still has the original candles. No candles have been given out. So the last person has piece of cake, and the size is blah 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 blah. I'm not gonna get into that. I'm not gonna get into that. That's crazy.
And in the situations like Grant discusses in this video, is more complicated than you want it to be. We need to be careful about probability. I think, in summary, though, what I liked about this problem is that we took a basic twig, turned it into a cake problem. There's a nice lesson about solving things in two ways, but there's also deeper water. And you get a glimpse of how mathematicians work. They start with a simple problem, and you realise that you tweak one part of the model, and things get more complicated. Hey, that's where we get our fun out of as mathematicians.
It wouldn't be super hard for one to do the mathematics of what the probabilities are once you decide your definition.
Correct.
You haven't done that.
I just haven't done it. Yeah.
But the problem is which definition is truly random.
Yeah, and that's the alarming thing, is it feels like surely that one of these is better, but it's not clear that it is. You need to be precise about how you're modelling the real world, because the real world is complicated.
What's your personal preference for?
So again, I would say you have to do a brute force, and that just means changing the area that it and stuff, and that area is the main.
What counts as the truly random cut of the cake?
Let me answer that by the pictures. If you look at these, it doesn't feel like this is distributing cuts fairly, maybe what we call uniformly. It feels like a random method. That's the random midpoint. This one, they're subtly different. This one is clustering towards the edges a little bit, but not as much as this one. Whereas this one feels like it's coloured in the circle. And that was me picking a random point by some method and a random angle. And maybe that double random application makes it look more uniform. It also backs me up and says it's roughly a third. But I'm really wary of saying that's the correct one, because it's tempting you want to believe the answers that you think are consistent. And there's no guarantee the reality works like that.
And who's to say that when you cut a cake randomly and do all the cuts, there wouldn't be like a little hole in the middle,
And actually, this is where probability questions.
Maybe the knife would touch the middle less often when you.
It depends how you're going to randomly cut it. If you've got, without briefing people on the complexities here, you just.
The standard distribution of cake allows and forces for there to be the cuts are always through the middle, and then you make the amount of cakes slices depending on the radiant of that. So it's always the middle, and then it's just a deviation from left to right on the circle as you go equals size of piece. But then some people are just inaccurate, and they end up with it being not the middle, but it's still mostly the middle.
Gave them a knife and a cake and said, right, I want you to repeatedly cut it at random. How would they do it? I think they'd hold it from one side and they'd just hack at it. And we know, actually, that it's not going to be random, because it's all going to come from probably this endpoint, and we're going to be spinning around here.
Yeah.
If they thought about it, maybe they'd do the double spinner approach and pick two endpoints, but that feels like a lot of work. Or you get what do they call it? A lazy Susan? Put the cake on it, spin that round, stop it, and then go. If this was cranked up to about 90 miles an hour, it would be a more random demonstration of picking a random angle to cut. Shall I close my eyes and wait until I have no idea where the candles are?
All right, yeah.
How long are we waiting?
Hang on, I'll do a tune you haven't seen as well, just to random up it a bit more. All right, let's see. Here we go.
The lengths we go to for maths.
Go ahead.
If I slice this down and miss and just break your turntable, how's that going to be?
Slice gently. Make sure you hit the cake.
Say when.
When?
We're done.
Yep.
Ah, we're between the candles.
You did it.
What are the chances? Don't answer that.
Just, only just.
Yeah, the point candle model was nearly not sufficient.
Now, Ben's got a deep video, and I mean really deep, about how he visualized and programmed some of this stuff on his own channel. If you'd like to check it out, well, there'll be links on the screen, down in the description, all the usual places.
Oh, I feel sad because, it just feels like the data points could be more easily, if you did a brute force program you would probably get the proper answer, and then the random distribution comparison doesn't give you a positive or negative, it just says what might happen actually versus the fullness of all genuine possibilities, depending on like how many differences of the amount of cake that you can have, whatever else. And like that can change some of it, but even if you have like pieces of cake that can be, let's say the minimum is a couple millimeters or whatever else, versus like centimeters, you're going to end up with similar distributions. But it was just something that's like, okay, no, I don't agree with some of the things, and then you change the method to both equals candles, and it's like, yeah, if you're going to cut from the outside, like, the thing about cutting cake, most people would say, is that you start off with the size of the cake that you would expect, and then with circle cakes, it just sucks. So you want to do a radial, and you don't want to do like a square piece instead, because square pieces for round cakes is just cursed. And then all of that, and it's a whole thing. And I'd be like, yeah, what did I say for this? Again, the candles, and then I said, it's not, this is not okay. You said the candles on each piece, the candles were on, yeah, the side empty. Yeah, I gave the feedback. Um, my conclusion is that I don't know what's going on. Yeah. What are the chances after he cut between the candles? Really, he got me. Well, okay, here's the thing, right? If you know ahead of time that the edge of the cake, and if you know where the edge of the cake is, you could aim for that, and then all of the time you're always going to get cake, and the other two are the candles. And then if you want to, then cutting in the middle means you're always going to get two candles, most likely, unless the candles are off to one side or whatever, which is the more genuine way of doing it or something. I feel like the random point of the random angle method most likely matches how I would approach cutting physical cakes into random pieces. Yeah, random point, random angle method. That is, yeah, pretty much. What are the chances? Don't answer that. Uh, oh, hold on. Exact thing in all four cases equal these ones. And a bonus where the distribution of the cuts wasn't in the video. Take two random points inside the cake, make a line, and then the result is 1/3 plus 35 something. What? Who are you? This is as an reader. For an interested reader, verify these results. Hi. Okay. I don't have the method to verify this results, but, yeah. What the heck n to the second, like, implies that your probability of 4 random points in the circle not convex. What the Okay, I'm getting off this. But it was just fun to have a thing where it's like um I'm not going to I'm just gonna look at something that I find is interesting and not say anything about it. And then I find something to say anyway. Because of course you had to change your methodology in the second video, and I don't like that at all. The numbers aren't um, related. They're a different thing. Or technically they should be inverted, right? Like, you can't have it so that, hold on. To be very real with you, right? In the line scenario, that means there is a 2/3 chance of getting between the candles, which was one scenario something which I don't know if I agree with or something. It's like, okay, 1/3 is the chance of you having it be connected, and then you have the thing about the other third, and I just can't help but think that it's invalid methods or something. I don't know. But I'm not weeding into this anymore. But that was neat. Um, Genuinely, I can find errors or things to be bothered about in anything. And in the end of the day, does it truly make much difference? Well, it kind of can, depending on certain things, because methods of thinking about problems that are faulty can lead to faulty um, ways of. Well, it made sense that if they said this is how you do it, they also said you couldn't um, trisect a line with a ruler and compass, and you can. Well, I'm not getting into that.